Uh, Good morning and welcome back, everyone. Let's continue with the course on continuous waves and trying to find them and their detection techniques. So today, I think we'll talk about searches in more detail. Alicia.
So thanks a lot. So this I will see here, don't get scared because the first many slides are going to go very fast. Is some material that is going to be made available to you. I just put it together quite fast yesterday. It's not covering all the material I've taught so far, but at least then you can have it for references. So just to show you, well, this is at the beginning, this support material. So I'm going to not to explain anything, it's just to flash that it exists. So you know, currently exists a full global network of detectors. So the results that I will be talking tomorrow are going to be the results obtained in the latest science runs by the LIGO and Virgo and KAGRA detectors. So the two most sensitive detectors are the two LIGO detectors that these have this shape of an L shape with arms of 4 kilometers. I just wanted to show because we are talking about this, but we have not even talked about the detectors. They are separated 3,000 kilometers from each side. So these arms are 4 kilometers each. Then in Italy, in Cascina, that is in the outskirts of Pisa, there is Virgo with arms of 3 kilometers. Then there is a small GEO, 600 meters in Hanover. There is KAGRA, 3 kilometers underground, Kamioka mine, etc. And hopefully in the future, nearby here, we will have the third LIGO detector. So these ground-based detectors, they cover a frequency range between a few hertz and several kilohertz. And there are several kinds of sources that we can see. We can only, with these ground-based detectors, we can only see sources that have like a stellar mass from a few times this, well, or from the even below the mass of the sun to several hundreds, maybe 1,000 times the sun, the mass of the sun, no more. Therefore, for these ground-based detectors, the only thing we will be able to see are either going to be the coalescence of compact binaries, either of neutron stars or black hole of stellar masses, or the mixture of them. That you have got, well, you have many experts here in ICTS with the source and the source modeling, and basically all the sources that LIGO and Virgo KAGRA have seen up to now are of this category. Then they could be bursts like coming from supernovae. They could be in a stochastic background that we are not going to talk it, like similarly that you have the microwave background, there could be a background on gravitational waves, either cosmological or astrophysical. And the topic of this conference are these continuous waves coming from potentially neutron stars. So these are persistent, long-lasting, and for this, since the signals is so weak, we are only focusing in these kinds of signals in our galaxies. We even have not seen any of them. So we are still hunting for them. They are expected to come from a spinning, non-asymmetric neutron stars. But as we also will mention tomorrow, will also be other exotic sources, like boson clouds around black holes, or other kinds of dark matter things that we could also reveal in continuous waves. Not necessarily at a single frequency, because of the spin down, other modulations, but they are very persistent, they are weak. And there is a number here of reviews, one in particular by Keith Riles, by Keith Riles, that is the other one, this is very nice, covering all this, the methods, the mechanisms, and so on. And I just want to point out, the reasons we are very interested to look for them is because if we see these gravitational waves, then we could get a lot of information from the neutron star. We will know a lot about this interior that Keith was describing. We could get information about the neutron star's equation of state, the interior structure, and we could be discovering maybe other exotic states of matter. We could have a better understanding of what's going on with pulsar glitches, accretion mechanisms, or other aspects of the life of the neutron star. Basically, all the searches we are doing are mainly focused on what general relativity tells us. But we could also check for deviation from general relativity using searches for pulsars. We could check if what is exactly the speed of gravitational waves, or also the existence of other polarizations. And that is also something that I will be addressing tomorrow. If at the same time we don't only see gravitational waves, but the electromagnetic waves, then the science we can do is huge, because having the information if the phase of the pulsar, if it's locked or not locked to the electromagnetic wave, then we will get extra information. And so all what we are talking is basically focused about neutron stars. But not only neutron stars can emit continuous wave-like signals. So as I said, they could be ultra boson clouds around the spinning black holes. And so far, this has allowed to probe a parameter space that was completely inaccessible by conventional laboratory particle physics experiments. So maybe we could even detect kind of new particles. And then there is something funny, that if we even think that dark matter could be like WIMPs particles, they will not be producing gravitational waves, but they can interact with the mirrors in such a way that they could push the mirrors, producing some forces. And the forces they would be doing in the mirrors of the detectors, then they could be producing like a movement and perturbation that then we will be confusing with a continuous gravitational wave. So what we'll be measuring will not be the gravitational wave, but we will be able to measure things that were related to this particle. And then there are like, that if we consider maybe primordial black holes of masses of asteroidal masses, then they will be spinning around each other. They will be far away from merger. And since they are so far away from merger, basically, their frequency will almost be constant all the time. And that could be in the frequency regime that we are interested. So these are kind of different things that when we are studying continuous gravitational wave, we could take up. So here just to show that, yes, the detector, the signals that we are talking is almost monochromatic at the source, but not at the detector. And this I wanted just to give you an image of, for example, what an antenna pattern here looks like. There are many ways to represent, but basically these blue spots here represent where the detector is blind. But this, as I said, since the Earth rotates, the detector rotates, whatever was this picture here, it just moves around, moves around, moves around. So basically, you have a dependency if you would just have one detector regarding which is the latitude where you are. This was explained. So this is just, as I say, your material, that the amplitudes are very weak. As Keith was mentioning, we search at F and also at 2F. Then he also has mentioned the process of the R modes. So I just leave you with the expression, given a certain R mode amplitude, these will be searches around close by to the 4/3 rotational frequencies. Again, they are going to be weak. Or it could be that we have a signal, neutron stars in a binary system that is accreting. And this is a fantastic system. Again, this could be generating gravitational wave around twice the rotational frequency. And of course, accreting matter is a natural method to power this gravitational waves emission. Yes, the answer is yes. All the students will have access to this PowerPoint. I'm not sure if it's already accessible or not, but this will be make accessible to all of you. And then I guess that Keith is going to talk about the torque balance theory that basically talks about that accretion is able to spin up the star, but then the emission due to gravitational wave will slow it down. So there is like a kind of an equilibrium, but of course you cannot control the accretion. And because of that, there could be some frequency wandering due to this accretion. So I might not have a very precise model for that, and that I have to take into account when I do searches. Well, these pictures you have already seen. So this is the band in which we could have be accessible. Not many we have, a spin down wind as explained. So just to show out that TF statistics is clearly also explained here. The time domain Bayesian analysis is also explained so that you have the equations and it's more clear than my handwritings. then the explanation that, and today. So now is when I start, I will slow down now. Okay, so what were the key points? We're looking for very simple templates. So almost quasi-monochromatic signals, but they are very weak. The pros is that they are very long duration. That means that I can gain signal-to-noise ratio by integrating longer and longer. The data for this kind of searches, I can assume that is very close to Gaussian, although it's not true, because I also have to account that there are many disturbances that particularly disturb continuous gravitational waves, that are this almost very narrow disturbance in the spectrum that I will show hopefully later today. We need precise frequency resolution from long-term phase coherence. The searches are going to give us we also for search, we have to look very precise sky location. And I just want to remind you that even with a single detector, we can have this very precise sky location, something that is not true when people are searching for these coalescents that are very short. There you need not only 2, but 3, properly localized in the sky. And why is this? This is because of these very long observations. As I was explaining yesterday, is because of these Doppler modulations that we can very precisely localize in the sky. Now, the computational costs for things that are unknown is really grows brutally with my total observation time, or at least with what I will define as my coherence time that I will talk today. So if I do a search, if I do much filtering, the cost of a search is just going to be proportional to the duration of the signal, of the duration of this observation time. The problem is that how many searches I will have to do, my template bank, for how many different parameters I will have to search for this signal, it becomes extremely dense with this time of observation. So that it becomes so dense, maybe then these optimal filters end up not being the optimal filters. So basically, the more information we have on the sources we are searching, the more sensitive we are and the cheapest they are. And when I have no information, the cost is brutally expensive and our searches become less and less sensitive. That was basically where I was stopping yesterday, and now this has been a plot very similar to what Keith has shown you before. So this was the spin down limit, assuming pulsars are gravistars, so that all the energy is emitted, all the radiation energy will be emitted into gravitational wave. That is completely not true, in particular for young ones. And then these were like the expected theoretical sensitivity levels for a full 1 year coherence integration, let's say at the more or less the current sensitivity, and in the sensitivity the detectors might have like 4 or 5 years from now. And as you can see, as Keith has said, well, we already surpassed the spin down limit for Krapp and Bala in using the initial LIGO, not this advanced LIGO, and by now we have already surpassed these spin down limits for 23 pulsars. So I was talking that there are coherent algorithms and incoherent algorithms. For the coherent algorithms means that we are just coherently integrated for a certain time duration. If my duration is short, let's say of the order of hours, not days, I would say hours, and that depends on the frequency, then I can consider my signal basically to be monochromatic. And as I was explaining in one of the first lectures, basically the best filter will simply be to do a Fourier transform. So for very short segments, what simply we have to do is that, to do Fourier transforms and to try to ensure that all the power of the signal will be within a frequency bin. In our field, then we pay a lot of attention to that. And then we not just work with data in time domain, but we work with data in frequency domain. And we have many ways to represent this discrete Fourier transform data. What you have been playing just with discrete Fourier transform is the simplest way, because we also store data heterodyne and so on at different frequencies just to reduce the amount of data that we have to work in different frequency bands. And there are a number of formats. We have what we call the short Fourier transforms, then the short Fourier transforms database developed by the Virgo collaboration, or even band sample data. So they basically, these are different representations that store the information in different ways, but have the same information content. Now, if we assume that this segment that we want to analyze coherently, it's much longer than many hours or of order of a day, then the power of the signal will have to spread several frequency beams. If we smear the signal, we lose the signal. What we want is to concentrate the signal. So now we have to already apply coherent methods. Ways to apply the coherence methods. One way was these F statistics that I was explaining you yesterday. Basically, you are demodulating, correcting the data for sky location, spin down parameters, etc. And you can do that for many different frequencies, and then you can store this information for a certain time, coherent time. This is one, the one that I was explaining yesterday. That is the optimal statistics already maximized over the amplitudes. Or there are other methods, like the 5-vector method. That is what I was saying. This is a different one, but basically, you just decompose all the information into 5 harmonics and you sum the information of these harmonics. Now, yes, we could use FF statistics integrating for the full run. That's possible. But I cannot do that if I want to cover all possible parameter space because my volume is huge. And if I know for a given point in parameter space, I can use any of these coherent methods. For fully coherent, I can use other versions of these FF statistics, or I can use this time domain Bayesian analysis that I was also described and is in these slides before, that I was also trying to explain yesterday. This is fantastic because it also does all the possible maximizations. And here are the references, in case you are interested, of all of them. Now, if I'm just looking for a signal from a single target, this is a very easy problem. It has no computational issues, and we know how to do it. And basically, our signal to noise ratio just grows with this time of observation, the square root of this time of observation. So when I'm integrating coherently, I will talk about coherent integration time. Excellent. Now, if I'm focusing, and the rest of my talk today is going to be on blind searches over using a large data set and over a large parameter volume, well, I have to search for many, usually different sky locations, frequencies, frequency derivatives, or many other nodes. So basically here the problem is that we have to be very careful and choose which is the algorithm we are going to use for this search. Because we have to be aware that the number of different sky localizations is going to scale like the frequency squared and with this time coherent squared. So the higher the frequency we go, the more I have to resolve in the sky. And the longer the segment is, the more I resolve. Then if the source is isolated, not in a binary, just using first derivative, the cost scales time coherent to the 6th power or more. So basically, given a certain computational load, so you get either a number of computers in the LIGO Virgo KAGRA clusters, or you apply to supercomputing facilities, and then you have a certain time and a certain computing hour that will be given to you, and that is what you have. And with that, you have to design the most sensitive search. That will imply that this is going to tell us information, for example, on how large this coherent time can be. There are also other considerations to be done. And if I would be wanted to use the optimal statistics, then this is going to limit that I can only use coherent integration times of a day or several ways. Must depend if it's a direct search, maybe it's 10 days. If it's an all-sky search, a day. Now, there is another problem. In many experiments, you hear that, oh, you have reached a significance of something of an statistics of 3 sigma, you have evidence, and 5 sigma detection. Well, if I'm going to search such a huge parameter space, just having pure Gaussian noise, given the volume of data that I have to analyze in this volume of templates, in pure Gaussian noise, we typically have triggers at the 6 sigma level. But in real data, we routinely produce triggers at 7 sigma level. So my definition of sigmas, we should try to understand what here means. But basically, when I'm going to analyze this huge parameter space, the idea is that I'm going to have plenty of outliers to deal with. Now, that means that I will have to design pipelines that are computationally efficiency, and also statistically efficiency. So one thing, I will have to design things that are not optimal, but not that far away from being optimal, that are robust and computationally efficient. Now, even if I insist that I will really like to do much filtering, optimal statistics, there are other effects that I should be taken care of. So because if I want to use optimal statistics with a very, very long coherent integration time, I will have to search over a huge number of templates. When I work over a huge number of templates, so if this was my distribution of the given a test, given the absence of signal, if I just have not so many templates that I search, in pure noise, well, the results will give somewhere here. I will just put a certain threshold at a certain false alarm, and I will be happy because basically everything will be fall below. But when I have this huge number of templates, clearly, I'm going to populate in my results. And even this area here, my false alarm was very small. If I do millions, trillions, or whatever number of templates, things will fail here. So that means, like, if we be doing a target search, for a target search, and just doing one template, I can put this threshold very low. But if I'm doing a blind search, if I just would like that at most for this search, I will get one trigger, that implies I have to put this threshold much far away. Now, there was the other plot that I was drawing, that was the distribution of the test given a certain signal. Well, if for targeted searches, I've put the threshold, I don't know, here, then this moves with the amplitude. So for targeted searches, these two distributions can be very close by. I will be able to distinguish. This means I can be able to distinguish signals with very small amplitude. But if I push this threshold very high up, means that I will only be able to see signals that are much stronger. So just of the effect of having more templates, more trials, because my template bank gets finer and finer, has the effect that is going to push the sensitivity. I have to push these thresholds, because otherwise I will have so many outliers that it will be impossible. And therefore, the search and as being not the best sensitive. So basically, what it says here, my detection threshold will need to be raised to maintain the same false alarm rate. And therefore, it decreases the sensitivity, because that was optimal just for one search. Now, we know that I'm just always talking about one detector, but I have a network of detectors. So if I would have 2, 3, 4 detectors of equal sensitivity, then if I analyze the data coherently from the different detectors, basically this is equivalent to integrate to increase what is this time coherence. Now, if I use data from one run, data from another run, and data from another run, this is horrible because the time between the start and the end is huge, and therefore that will imply that I have to refine a lot my grid in parameter space. But if I use the data of one run, but of several detectors that are running at the same time, somehow my sensitivity increases, like if I would have increased the data n times, but my parameter space resolution is not increasing. So for me, it's better to have more even if I could claim a detection with a single interferometer, for me, the more detectors are operating at the same time, it's better because I increase sensitivity, but I don't have to increase the grid in parameter space. So let's move to these semi-coherent methods. So what's the idea? Given that I cannot do a full coherent search over the total observation time, the method that we do is that we simply split the full observing time into segments. Each of these segments, I do a coherent integration. That this coherent integration could be something as simple as simply doing a Fourier transform, or doing an F statistics, or doing things sophisticated. And then I just have to come with some other statistics that will allow me to combine the results from the different stretches. And that's the full idea. And then we have a full zoo of methods to do these kind of things. So basically the idea is if I was having the full duration, I make chunks in each, if it is short enough, so for each chunk, let's say an hour or half an hour or a few hours, I could simply do a Fourier transform. So first hour, second hour, third hour, fourth hour. Then I will have information in frequency. And the issue is like this, the signal is going to be changing frequency over time. And I just have to find some way to trace what I should be summing and at which frequency they have to be. Okay. In these cases, the signal to noise ratio grows as the time coherent to the square root of the time coherent as before, but also grows with the number of segments, usually to the power not 1/4, but a lower number, 1 divided by 4. Not always exactly, because that depends on the method. Not necessarily. So here, I could be analyzing the data. Usually what we do two things, depends on the method, is that I don't care if the data, well, you take all the data. To do this analysis, the difficult part is like while other analyses, they are taking data and doing searches, we always have to wait until basically the data is all there. So to analyze every single template, I need that the run is finished, or, well, now was operating for run. That run is cut it into 2 pieces. So the first 6 months is what now I am busy analyzing, but I got to wait until this data taken was finished, it was clean, it was properly calibrated, and then I have data from where? I have data from LIGO Livingston, LIGO Hanford, and Virgo. Virgo will only be able to contribute at lower frequencies. I could use the Virgo data to analyze all the frequencies, but the more data I put, I increase the computational cost. But I can use it for targeted searches and in the frequency bands in which Virgo basically competes with LIGO. But typically, for my particular searches that I use, I always use the data from Hanford and from Livingston. They are not always operating at the same time. So somebody will have to give me a list of segments per every detector when this data was good, when the data was bad, or when the detector was offline. And then we will be constructing stretches. Let's say typically we construct the stretches of half an hour. And from there on, we can construct longer stretches, either by combining to produce just a longer Fourier transform or something different. Then the method that we choose for this coherent integration, we can analyze it separate per detector, or we could already combine the information from different detectors. The pipeline that I'm using analyzes the data separately, but I put them all together. It's a matter of choice. I can do single interferometer searches and multi-interferometer searches. And basically, it's like I just need to label what is this time, that is an interval, and these frequencies. I need to label more things, because in order to trace which is this evolution, I need to know from which detector this information was coming. Because the evolution is going to be different, because they are located in different places in the Earth. So, yes, and we can do consistency test, we can do coherent analysis among different things. So there are many things we can do with this data. So, of course, if I just do a target search just for one template, this approach is going to be less sensitive for the same amount of data, but it could even be much faster. These methods also allow me to analyze all the data. And actually, if I say that I have a fixed computing cost, I can design that if I want to analyze the full certain parameter space volume, and then if I fix, this is the computers that I have that I can use for this search, these end up being more sensitive than my optimal statistics. And this is always the problem. I want to cover a certain sky region, that could be all the sky. I want to cover a certain frequency band and a certain frequency derivatives, and they tell me this is the cost I have. Design the search. So basically, these are good because I maximize sensitivity, because I have to organize these template banks. Of course, I have to choose how many segments. I have to choose the durations of the segments. And then is, depending how I combine, I do different things. These approaches, there are a full zoo of them. And here, I hope that in the PowerPoint you can read it better. you have basically all the references to all the techniques that have been developed. These techniques, these incoherent or semi-coherent algorithms, they can categorize as basically depending on the kind of statistics that they use, that they do non-statistics, they just look for coincidences, or they just look to some power, or to put some thresholds that I will explore. You will hear a lot because I'm working on half transforms, and I will explain you that in more detail. There are also things looking for correlations, and some in power with some weights, depending on the sensitivity or depending on the noise level. And there are also some other classifications of all the zoo of codes that we have and pipelines, depending on how many assumptions we do on the signal model. And there are these loosely coherent or cross correlations. There are things that even make no assumption on the model, that are basically things that can accommodate from this frequency wandering. Basically, the picture that I showed you before about this accreting mechanism, then this exact power Taylor expansion might not be very accurate, because then suddenly there are some changes there. Then there could be some other methods. Of course, if the less information you put, the less sensitive they become, but they could become more robust to grab these kind of things. And of course, they could even be things like, oh, and if the source is in binaries, we have the volume of parameter space suddenly blows up, because at least you will increase the dimension in 3 or more. And then here, well, I also have been developing another one based on half transform. This is also half for binaries that can work with them, that I will talk about them. So the main differences was that, okay, so the idea is that you get in a stretch of data, you pass it somehow into the Fourier domain, and now we have to design some statistics to sum across. The first 3 methods that were developed a long time ago, and they were already used by the LIGO collaboration in 2008, analyzing what was data from a certain run. Okay, so these are plots from 2005. Basically, were these 3 ones. There was something called Stacker's light, power flux, and half. What were the differences? Is that, for example, Stacker's light basically was simply summing normalized power. You remember the exercise that you were involved yesterday? You were having the x divided by the n. So basically, this is the normalized power that then you will sum across a certain tracks. Power flux is was like or the original power flux was a modification of this one. That was to sum the power, but also including some weights. And these weights was having information both on the detected noise and the antenna pattern. Because it could be that in a certain frequency, well, at a certain times, the detector behaves better and sometimes worse. And this is frequency dependent also. Suddenly there could be a plane flying on top of the detector, and then you have a disturbance or many other things. So there you identify which periods are more noisy, and therefore you put a weight so that it counts less. And as you saw, the antenna pattern has a certain shape. So for the same sky location, you have times in which you have very good sensitivity and times in which you might be completely blind. So the times in which you completely are blind, you could multiply almost by things close to 0. And when you are very sensitive, you can push it. That is similar to this, what this optimal statistic was doing. That was dividing by the noise. So basically we can wait, and we can wait with noise that have information regarding the amplitude antenna patterns and the noise. And then half is funny. You will have enough because I will explain that in more detail. What it does is it computes this normalized power and then decides to digitize. puts the thresholds, and then you have simply ones and zeros. And then you sum ones and zeros. You can just sum ones and zeros, or you can sum ones and zeros with some weights in the same way as power flux. Advantage of half is that these other methods sum power, but suddenly here I have a huge disturbance. These methods will sum a huge number. Maybe with some ways that will downgrade it, but will add a huge number. And therefore, in my statistics, this will be a huge number. We'll say, hey, it's a potential signal. In the case of half, I don't care if it's a reasonable number or a huge number. I put a threshold and I mark it as 1. So if here I have a huge disturbance, only contributes 1. It's not contributing huge. That means that this method is very robust when my signal is noisy. And this always, when we have many pipelines, and we always do comparisons, even in these very old dates. And then basically this is how sensitive we are at different amplitudes. And this is the efficiency of how many signals at a given amplitude we're able to detect. So power flux, this was a comparison of these three. Power flux is the curve on top. So this was the most sensitive. Of course, half has to be the last, because if I have digitized, means I've lost information. If I lose information, I lose sensitivity. But not by much. Maybe I lose 10, 15% of sensitivity. Oh, that's a lot. Yes, that's a lot. But when I have a disturbed band, this, that was the one giving me the best sensitivity, did the worst, and half was the best. This is a story of comparing pipelines. Oh, well, and this is, just to have an idea, this is a half map of a hardware injection. And since this was a run of just 1 month duration, you cannot localize it that well. Much later, this was a paper published in 2016, but using the data, 15 months of data of a certain, still initial LIGO run of 2009-2010, we did something else, but using a full zoo of pipelines that we were using, because it's good to have more than one pipeline to do a search, but it cannot be that every group develops a different pipeline and everybody wants to do searches, because these are very costly. You have to select which one can run or not, in particular in the collaboration computers. So there are things like a sky half, frequency half. So there are two versions of half. There is the power flux. Then there is this time domain F statistics. So another variation of F statistics working in time domain. Oh, and there is something called Einstein at home that I have not talked about it, and I'm not sure I will mention, but basically are you aware of SETI at home? No? SETI? Looking for extraterrestrial life? And that they were using voluntarily computers from maybe any of you. So any of you on your phone, on your tablet, on your laptop, whatever, you can install Boeing, and then you can donate your cycles to whatever project you prefer, LHC, weather prediction, maybe even BBC things, to search for extraterrestrial life or to search for pulsars. So this was a project that started within the collaboration. Now it's a project that is still working, but is out of the collaboration, run by Max Planck. So now this is computing cycles competing with us. And we can get more computing resources outside the computers of the collaboration, so we don't have to pay the electrical bill, not the air conditioning for them, to get results. So then you will get very computing cycles. And then basically these are two plots of, again, a quantity is called sensitivity depth. So more depth, more sensitive you are, and the efficiency. And okay, so Einstein at home was the most sensitive one. And the second was my beautiful half, I code. And then there were the others. But suddenly, if we go in a band in which there were some line noise, the beloved Einstein at home ends up being the worst, and I was still performing better than the rest. The performing means if you are able to identify there is a signal or not a signal. But another question that is important is when you identify something and you return it and you give it, and then it has to be followed up, it comes with error bars, the uncertainty. And here there are the uncertainty in errors per second. Okay, in the spin down, for example, for the different searches and the ones that got the smallest box were the two halves. Or these are radians. Okay, in one sky location, in the sky locations, the ones with the smallest box, I would say my beloved pipeline, and then was coming, well, instant at home, the other ones, but some other ones, the time domain F statistics, that was going, oh, this is horrible, horrible error bars. Okay, so I said that there is this full zoo, and I apologize because I just stole this material yesterday for one of my master students of many years ago, and now things are in Catalan, but you are used to many languages. So don't read, I will just look at the numbers and the equations. So what is half transform? This is a robust technique invented at CERN to search for traces in bubble chambers. And with this, you can try to find anything that can be parameterized. It's very simple. So let's first explain an application of the half transform to search for lines. So basically, if you have a line given by this expression, y equals ax plus b, and we can plot this line in this plane, in the plane of your data, and this is my line. So the half transform, what will be, is transforming from the space of my data are going to be the sets x and y, into the space of the parameters a and b. So this line corresponds to this point, 3, 1. So this is what we want to transform from data to parameter space. Now, if I have just one point here, given one point here, I can try to check to how many lines this would correspond. This would correspond to an infinite number of lines, and in the space, or in the parameter space, then this point here translates into one line. These are all the possible values of A and B compatible with this point here. If instead of having one point, I have many points on this line that I have considered, then each point here will correspond to a line in the parameter space. And which is the value of parameter space of this line here? It's clear. It corresponds to this intersection. So in this point here, it should have been crossed by as many points of the points that I've been considering here. So basically, this is what we do. I'm going to convert points in my time frequency plane. I'm going to convert it into points in my parameter space. Now the problem is that my data is going to be digitized. Well, we have already started with the digitized x and y, no problem. But my parameter space of A and B's, I cannot resolve infinitely. So my A's and B's will have to also to be discretized. And my x and y are also discretized. So a value of x is not an x, it's a certain interval of x. And a value of y is also an interval in y. So for each of my points, it will not correspond to a line in the AB plane, but it's actually going to correspond, not to this, but to a certain region, because of this uncertainty in x and y. Now, I also have to have uncertainties in A's and B's, this little grid that you see below. And therefore, when I'm drawing, every time I'm drawing a line, it's not going to be exactly a line. There will be a number of places, a number of these boxes that I will mark. And I can mark with a +1. So this is the story of the half transform. And I can add +1s, or I could add weights. And the weights that I can add, so in the half transform, instead of summing the ones or zeros, I can sum ones and zeros multiplied by a certain weights. And these weights are going to be something that they will be related to the noise in a certain frequency bin, and is going to be related to the antenna pattern for the certain scale location of my interests. So this is the basics. Does it sound easy? And as I said, well, then how does it work in practice? Well, this is a very robust parameter technique, and you can use it for many things. It's just that whatever you search should be parameterized, because it's a transformation from the manifold, if you want, of your data to the parameter space. Okay, so basically the idea is that we will try to find the patterns produced by both the Doppler modulation and the spin down of the gravitational wave signal in the time frequency plane of the data. All basically is controlled by this Doppler effect formula that, given the frequency at the detector, this is related to the frequency, let's say, as received at the solar system barycenter with the Doppler shift. And this, how much this changes, of course, this will be the relative velocity between the detector and the source, and this is the point in the skies where the source is located. For a given time, I can consider that this value is fixed, and therefore it just produces me a drift. And when I change time, then this is going to have a certain frequency evolution that depends on the spin down. So basically, if I'm looking for isolated neutron stars, I'm going to have patterns that simply are going to depend on n, sky location, so alpha and delta, and then frequency and frequency derivatives, as many as I would like to consider. The process: I grab the full amount of data, I make chunks. It's not exactly that these chunks is TOPS divided by n, because there are going to be gaps in the data, but let's ignore the gaps. If I take the data stretches to be short enough, an hour, 2 hours, an hour, 2 hours, some minutes, it depends what I'm exactly searching for. I can simply do a Fourier transform. I can compute the power of the Fourier transform, and I can, what was the quantity? I have the normalized power. So I compute the normalized power. I put a threshold. So I define a threshold on this. The threshold that I'm going to set is going to be 1.6. And I'm going to set 1.6, because I will explain you, because that means that if I would be having Gaussian noise in my data, that will translate into that I will be selecting 20% of the points in the plane of the time frequency plane. So I put a threshold, and any point for each segment, I do the Fourier transform, I compute the power, I normalized, somehow I just have whitened the data, I put the threshold, and every point that passes this threshold, I mark it with a 1. And if it's below the threshold, I mark it with a 0. Okay, now what would happen is that I will have these zoos of 1s and 0s, and then I just have to find which is going to be the frequency evolution of the signal for the certain point in parameter space, certain frequency derivatives, and a sky location. So along basically this track, I will just go along this track, and I can sum 1s and 0s, or 1s and 0s multiplied by weights. And for that point in parameter space, I will count this sum, this n, and then I can produce an histogram in the space of the parameter space. Then I could end up putting, if you want, another threshold, and I would say whatever crosses a certain threshold are my candidates. There are many ways to implement that. And as I say, I can sum 1s and 0s, or I can sum weights. And then here, of course, what we want is something that is sensitive. And I've been talking about two thresholds, the threshold of peak selection and the threshold in order to say I have detected things. And this I will, by the end of the class, maybe hopefully explain you how to select by maximizing the significance or critical ratio, or by applying the Newman-Pearson criteria that's to both minimize false alarm and false dismissal. So it's clear that if I always I put the threshold very, very, very high up, so that I don't want to select noise, well, I will not select noise, and I will also not select points of signals, because my signals are very, very weak. We're always working in the regime of very weak signals. So if I select too little, I will not even select the signal. I will lose the signal. But if I select too many, if I put these thresholds very low, that I select too many points, then I will select almost all the points. There will be no difference by when I have the signal as well. So there is a compromise on how many points should I be selecting. And the optimal is 20%. Careful, this slide has mistakes. So everything is related to statistics. So I have to know which is the probability of selecting a peak, and the probability of selecting a peak in the absence of signal is E, and there is a minus missing here, this threshold. Because this, in case of Gaussian signal, when there is no signal present, my chi-square distribution with 2 degrees of freedom was the exponential distribution. So, and the probability of selecting a peak, if there is a signal present, depends on the amplitude of the signal. So basically, it's a modification of the quantity before, time plus here, this term here, that depends on the threshold and the amplitude. And this amplitude of this kind of non-centrality thing, it depends on the amplitude of the signal. Okay, if I ignore, so if I have my data, I have n stretches of data, because I've done n SFTs, the maximum value of summing across a certain path is going to be n. But I would like to know which is the probability of having gotten a certain count. if I just sum ones and zeros, this is a binomial distribution. This is the binomial distribution of having selected n points and not selected n minus n. Because we know which is this distribution, it's very easy to know what is going to be the mean value when we only have noise. That is going to be this n and the probability of having selected peak, and its variance. And when there is a signal is present, this gets a bit increased, and the variance also gets a bit increased. And from here, we can define what is the so-called critical ratio or significance or I call it significance, that is the number count minus the expected mean when you just have noise divided standard deviation when you just have noise. If instead of summing ones and zeros, I would have summed things with weights, then it is no longer a binomial distribution, it's something much more complicated, but when we are working with very, very, very large numbers, things can end up being approximated by a Gaussian, in which if you control what is the means and the variance, then you can just use that. When I know what is my outcome, then I can define other quantities. I can then compute, because this will be the result of my test, I can go back and compute what will be the probability of false alarm and what will be the probability of fast dismissal given a certain threshold. So I can then compute that the probability of the full half, not of selecting a peak, but a full half, given a threshold, given the other threshold in pixel selection, and given a number of how many stretches of data I have, basically this is the sum from n equals threshold or the integral, depends how you prefer, of Pn given a certain threshold, zero amplitude, and the false dismissal, again, given a threshold, the other threshold, the amplitude of the signal, and how many stretches we have, then this is the sum from 0 to n, let's say threshold minus 1, the probability of having obtained n given a threshold and a certain amplitude. And basically, by minimizing these two, is when one can find which is the threshold that I have to put to say I have detected things, and which is the threshold that I have to put to select peaks in the first place. This can be done even analytically, making approximations all over the sky. And then from there, one can get that for this particular kind of search, let's say the 95% upper limit are going to scale in a certain way. Well, it doesn't matter. I don't put this question. It's going to be scaling like things like the expressions that I given you before. That depends on the duration of this coherent integration time and the number of segments. When we have that, and we have either we think we have detected things or not. So far, we have never found anything that end up being realistic. Then we have to put upper limits, because we want to do science, we have to know where we stand. And then I could put, or I can try to find my upper limits, basically following a frequentist approach. In a certain search, in a certain frequency band, I might have gotten my loudest event. My loudest, after having analyzed a full parameter space, I got my loudest number count. And then what can I do is to try to find which are the probability distributions of having contained a certain number count given a certain amplitudes of the signal. I can do many, many, many injections until then I find at which level I have to do, with which amplitudes I have to do these injections to get that if I would inject signals stronger than this value, I would detect them at least in 95% of the times. And from there, we can get many things. The injections, they have to be done doing Monte Carlo injections, covering the full parameter space. So the upper limit, sometimes we put upper limits populated base without any information. We use uniform, not priors, but uniform distributions. Or we could try to find upper limits for linear circularization, linear polarization, circular polarizations, or others. Of halves, there were several pipelines going around. Because the way that I've been explaining you the half was like the brute force. You will take a point in parameter space, you will try to follow the track, and then you will get the number count. Oh no, we can do things many more sophisticated, taking into account the symmetries and the properties of just this equation, the Doppler equation. Because basically, every time I do a Fourier transform, I get a stretch of data, I do a Fourier transform, then basically I will return values in the Fourier domain. But each value that I return has information. So this has information a certain delta frequency. So if I say that I have a peak at a given frequency, that peak will belong to, let's say, fk minus delta f divided by 2 to fk plus delta f divided by 2. The tracks depends on the sky location. So basically, when the velocity vector is orthogonal to the sky location, this gives me a 0. And basically, there is no much Doppler shift. So that means that the sources of my ecliptic in the ecliptic pole, basically they are going to have very little variation. Sources that are in the equator, well, in the equator, sometimes this is going to be parallel. So I'm going to have the maximum. And sometime later, maybe it's 90 degrees, even if it was at the equator, and then it has the 0, and then I see the maximum modulation. So you see that this modulation really depends on the sky position. Now, basically, given a frequency of the signal, how much gets modulated depends on where in the sky, which is the angle in the sky. So this is a horrible picture here, but if this is the velocity vector of the detector, or the relative velocity between the detector and the source, if the difference between this and this is a certain value, this tells me a certain angle. So given a certain f0, if I have a peak, a 1, selected at a certain frequency, then that means that this corresponds to a full circle in the sky. So a full circle in the sky There is a full circle of locations compatible in the sky, compatible with this difference in frequency. If my frequency at the detector is not just a fixed frequency, but it's a little interval, then that means that I have a full annulus of sky locations in the sky that are compatible. So for a given time, I'm going to have all these annulus. For my next data segment that I consider, the Earth has moved, the velocity vector has moved, and the orientations of these circles moved. And when I used, let's say, several months of data, I got all these possible orientations in the sky, and then I can search for the intersections of all these annulus in the sky. And then there is funny things, like for each time stamp, I can compute all these circles. I can compute things that what I call partial half maps. And I can make this code very efficient computationally because the different peaks will produce different annulus, but I can register them in lookup tables, and then I just have to mark for different frequencies. And then when I change the time, if this was not fixed at a fixed frequency, but it was having certain frequency evolution, I can sum the information that I've computed. If this is always constant, no spin down, I just sum. And if it has some spin ups, spin downs, or whatever, I just have to sum different maps. So this is the most efficient kind of code that we have to do blind searches. And this is the kind of implementation. This is explained very badly. I apologize for that. For half. And then there is another group in Rome that they have a frequency half because they use some other symmetries to spin it up. I switch off the computer now. And I want to explain you a number of issues that are very important. So, the choice of the coherence, because there are restrictions in how we are going to choose this time of coherence. I said, for example, if I just want to do a Fourier transform, my frequency resolution of my frequency bin, then is going to be 1 over T coherence. And if I'm going to put these thresholds to select peaks, I better select the duration of this time such that all the frequency, all the power of the signal is within one bin. Because if it goes to many more bins, then when I put this threshold, I'm going to lose it. And I can think of thresholds because of half, but the same with all the other methods. If the signal gets smeared in several frequency bins, it's lost, or it gets downgraded. What I want is to use that a duration such that it is all contained in here. That means that my total, and I don't care how much this has changed from the frequency at solar system barycenter. What I care is that in a small interval, this does not change so much. For sure, if this was the F0 of the source, this is the total variation. But I just want these variations to be small. Okay, so what I want to ask is that the total variation during the duration of this segment, I would like that it's smaller, and usually we demand that it's smaller than half a frequency bin. Okay, from here it's easy to derive that my coherent integration time that I should be using should be then be smaller than 1/2 1 over the maximum change in frequency that I have. The magic equation is that f of t at the detector minus f of t, let's say at solar system barycenter. This was solar system barycenter v t n over c. Usually, for isolated neutron stars, this is going to be the dominant effect. The dominant effect is the Doppler. It's not going to be the spin down of the signal. So basically, my change is going to scale like f c dv dt n. This is going to be smaller than this f c dv dt. So what is important here is not the velocity, but actually the acceleration. And as you can imagine here, what is the most important contribution is actually the acceleration due to the daily rotation of the Earth. Even this is the one that velocity was the smallest of the two components, but the acceleration is the important term. So my f dot max, if my contribution, the strongest contribution comes from the acceleration of the daily rotation of the Earth, I can compute it like velocity of the Earth square divided by the radius of the Earth. So basically that gives Fc for pi square rotation of the Earth divided by the duration of the day, and this is the radius of the Earth. So by putting these numbers in here, end up that my coherent integration is going to be smaller than 50 minutes, 500 hertz divided by f. So if I really want that the signal does not spread more than half a frequency bin, means that at 500 hertz, I can only do coherent integrations of 50 minutes. If I'm at lower frequencies, I can integrate much longer. And if I will be analyzing frequencies at higher frequencies, this would have to become smaller. Next issue. There was this beautiful plot. Horrible. Quite horrible. Well, of the annulus. And maybe you have realized that what I'm trying to do the drawing is here that the annulus have different thickness. Because these are my bins. So they produce different separations, and there is going to be that equation here. So basically this equation here, I can just write f of t vc cosinus of this angle. And I would like to have an idea of which is the thickness of this annulus. How can I derive? Well, the thickness of this annulus, my thickness, basically goes like CV, my resolution in frequency, and the sinus. which are the most refined? The most refined is when this will be 1, and that is giving me which is my frequency resolution in the sky. So basically, I know that my frequency resolution depends on the frequency and also with the duration. So the higher the frequency I go, the thinnest becomes thinner and thinner. The thickest, well, the thickest, of course, if I divide by 0, this becomes an infinite. It doesn't work really so well. What I can go is in the limit in which this will be also delta 3. And from here, the maximum thickness, then you can easily compute. But basically, from the thinnest is what I'm getting the resolution in my parameter space. So I already got coherent integration. I have my frequencies. I have a scale location. Oh, the spin downs. Which will be my resolution spin down? Of course, all what I'm saying, there is a very elegant way to compute. The metric, set a certain mismatch. But the mismatch was for coherent integration. It's not easy to compute the metric for semi-coherent integrations. And that's when we are always going to like to this educated guess. And then we can compare to these metrics. But this will be full lectures about how to compute properly these metrics using these alternative methods. But the approach is always the same. If you can try to compute the metric of in the parameter space, and then you set which is the mismatch you want, that will give you the grid. But if not, we do these educated guesses. The spin down, well, from the spin down, I just have to write which was the evolution of the signal. So if I'm assuming that the signal it starts at a certain reference signal plus n equals 1 to s fn n factorial is 0. So if I do a Taylor expansion, well, it's very easy. It's very easy to see which will be the grid in every spin down. Because basically, this is going to give you a path. You can consider each term completely isolated. You can ignore a little bit the corrections. And basically, the way you compute is that we were having a certain total observation time. Given T coherent, we have a certain frequency resolution. And basically what we are asking is that how much we have to change a certain value so that in the full observing time, let's say of the full year, will change you one frequency bin. Then from here, one can deduce that the resolution, depending on the order of the spin down, is just n factorial, the discretization in frequency divided by T ops to the n, or if you prefer, n factorial, and this is 1 over T coherent, 1 over T ops to the n. The question is also to know at how many spin down parameters we need to use. And the how many spin down parameters do we need to include is going to depend on the age of the pulsar. And also, which frequency range we want to cover. So apart from knowing which is our resolution in each grid, we need to know which are going to be the values of them, and the values of them depends on the age of the pulsar. How many spin downs to include? We have to include as many spin downs needed as far as the discretization of Fn, this gets smaller than the Fn max. If the discretization is always smaller, you have to search for this spin down order. As soon as the discretization becomes larger than this value to be checked, then you have to stop. And what happens here is that, for example, for a pulsar 40 years old, at a maximum frequency of 1 kilohertz, the X-man value ends up being 3. You will need to include 3 spin down parameters. While I was having some numbers here, but I think my time was over. And since my time was over, I guess I have to stop here. And I can continue from here tomorrow, if there are questions. And tomorrow I will continue with kind of follow-ups we do, and explaining also then the results that we have obtained within the collaboration.
T-coherent and T-observation to be same.
No, only for when you do a fully coherent search. T-ops is the total observing time of a run, that typically will be several months or a full year. And this T-coherent is like, for example, I use for some searches minutes, for some searches half an hour, for some searches 2 hours. Other people for doing direct searches can end up being a day, but it's not going to be much larger than that. And for a targeted search, T-coherent and T-ops is the same.
Any other questions? Maybe online participants have questions?
My plan, but I've gone very behind, is that I was planning to deduce analytically the best way to look for thresholds. But I would say if you go to my paper of 10 years ago, I think the people can be like an exercise to read it, how these thresholds were to be selected.
Okay. So if not, let's thank Alicia. We'll be back at 2 o'clock with the tutorials.